You see that fuzzy dot racing through our solar system at 130,000 miles per hour. Third interstellar visitor ever confirmed. Discovered July 1st, 2025 by the Atlas telescope in Chile. Everyone called it massive. Early estimates screamed 10 to 20 kilometers wide. Then the measurements started coming back wrong. Hubble aimed its sharpest eye at this thing on July 21st. The nucleus vanished, not gone. Hidden. Buried under something so bright, the most powerful space telescope in orbit could not punch through to see the actual rock underneath. 440 meters to 5.6 kilometers. That is the range. A range so wide it tells you almost nothing except this one fact. The nucleus is surrounded by a cloud so reflective, so active, that it makes itself look like something 10 times its actual size. Also, comment from which city you are hearing this from. Also, this script is researched and factual using sources from David Jewett's Astrophysical Journal Letters paper on Hubble Space Telescope observations, published August 2025, and Martin Cordner's JWST detection study from the same month, archived on Hyperactive, showing carbon dioxide. Dominance both peer-reviewed and observationally verified. Now back to the information. Atlas found it 420 million miles from the Sun, moving retrograde, tilted 175 degrees to the ecliptic. Eccentricity 6.143. That number means this thing is not coming back. Ever. It punched into our system from interstellar space, and it will punch right back out. Perihelion, October 29th, 2025, 1.36 AU. Between Earth and Mars. Closest approach to Earth 1.8 AU. 170 million miles. No threat, just passing through. July 1st. Discovery images show a bright fuzzy blob, not a point source. Already active at 675 million kilometers out. David Jewett and Jane Liu used the Nordic optical telescope on July 2nd. Confirmed diffuse appearance, clearly active. Miguel Alarcón at the Instituto de Astrofísica de Canarias used the 2-meter twin telescope same date. Found cometary activity, reddish coma, dust grains, similar color to TII Borisov, tholins, irradiated organics. The signature of something that has been cooking in cosmic radiation for a very long time. 2 months before anyone noticed, 6.4 AU from the Sun, already outgassing. The coma was growing before anyone was looking. 46 kilometers if you assume 4% albedo and all the light is reflected sunlight bouncing off a solid nucleus. That would make it enormous. Larger than any interstellar object by an order of magnitude. Larger than 2 I Borisov, by a factor of nearly 100 in diameter. The statistical odds of finding something that rare as only the third interstellar object. 0.0001, 1 in 10,000. Avi Loeb at Harvard pointed this out immediately. If 3 I-Atlas is truly that big, then the population models are completely wrong. We should have found 100,000 small interstellar objects before stumbling on one this massive. The wide field camera captured what David Jewett calls the sharpest image yet. Teardrop-shaped cocoon of dust, sun-facing plume, hint of a tail. But here is what matters. The nucleus itself cannot be directly seen, even by Hubble. The coma brightness accounts for a large fraction of the apparent brightness. Maybe 99%, maybe more. If 99% of the light is scattered dust, then the nucleus is 10 times smaller than the early estimates suggested, 5 kilometers. If more than 99% is dust, then smaller still. Total dust loss, 12 to 120 kilograms per second, depending on particle size. At 2 AU distance, 180 kilograms per second total. Compare that to TII Borisov, 70 kilograms per second at the same distance, more active, but the activity per unit surface area. That is where it gets strange. The dust production rate does not change with assumed size, 180 kilograms per second either way. So if 3 I-Atlas has a large nucleus, then it has very weak activity per square kilometer of surface. If it has a small nucleus, then it is hyperactive, blasting out material at rates that match or exceed normal solar system comets. Effective radius of nucleus less than 2.8 kilometers, assuming red, geometric albedo 0.04. Cannot be directly resolved. The bright central region in Hubble images includes both nucleus and inner coma mixed together inseparably. Lower limit. The nucleus cannot be smaller than 0.22 kilometers in radius if the coma is supplied by sublimation of carbon monoxide. Must be larger if a less volatile molecule drives mass loss. 0.2 to 2.8 kilometers radius. 0.4 to 5.6 kilometers diameter. Compared to Oumuamua, estimated at 0.2 kilometers wide. Compared to TII Borisov, estimated at 0.6 kilometers. 3. I-Atlas falls somewhere in that range. possibly smaller than early hype suggested. Definitely not the 46-kilometer monster. On July 21st, the coma of 3I Atlas measured 26,400 by 24,700 kilometers, according to images from the 10.4-meter Grand Telescopio Canarius, twice Earth diameter. The coma is not just big, it is bright. Dust scatters sunlight. Makes the whole system glow. When you look at 3I Atlas from Earth, you're not seeing a nucleus. You're seeing thousands of tons of dust reflecting light back at you. The nucleus is a point source buried inside a diffuse cloud. Hubble resolution 0.05 arcseconds. At the distance of 3I Atlas in July, that translates to about 100 kilometers per arcsecond. So 0.05 arcseconds is 5 kilometers. The nucleus, if it is 1 kilometer across, would subtend 0.01 arcseconds, below Hubble resolution. It would appear as a single bright pixel with no resolved disk. Even at 5 kilometers, it barely reaches the resolution limit. The coma extends for hundreds of pixels in all directions, optically thin, transparent, but bright enough to dominate. James Webb Space Telescope turned its near-infrared spectrograph on 3I Atlas. 3.32 AU from the Sun. Martin Cordner at NASA, Goddard, and Catholic University of America led the team. Results published August 25th, 2025. The spectrum shocked everyone. Carbon dioxide dominated coma. CO2 to water ratio 7.6 plus or minus 0.3. Revised to 8.0 in later analysis, highest ever observed in a comet between 3 and 4 AU, 6.1 sigma above the trend for long period in Jupiter family comets. Only one other comet approaches this. See 2016, R2, an outlier, known to be chemically bizarre. For all other comets, the median CO2 to water ratio sits around 17%. Bulk ice in comet 67. P. Churyumov-Gerasimenko measures 7% CO2. Typical solar system comets sublimate water much faster than carbon dioxide at the distances. 3I Atlas occupied during observation, but 3I Atlas flips the script. Carbon dioxide pouring out, water barely detectable. The JWST data shows carbon dioxide emission band at 4.3 micrometers. Extremely strong. Water at 2.7 micrometers. Present but weak. Carbon monoxide at 4.7 micrometers. CO to water ratio 1.4, more typical. Carbonyl sulfide detected. Water ice detected in solid phase. Dust continuum. But the CO2 dominance stands alone. Why? Intrinsically rich means the comet formed in an environment where carbon dioxide ice was abundant relative to water. Near the CO2 ice line in a protoplanetary disk, or exposed to extremely high ultraviolet radiation that processed the ices. Radiation can break water molecules, strip hydrogen, leave oxygen-rich compounds behind. Carbon dioxide survives radiation better than water. If 3I Atlas formed in a high radiation environment near a massive star or in a stellar nursery with lots of UV flux, then the ice inventory could be CO2 heavy from the start. Suppressed water sublimation means the nucleus has a thick insulating crust. Heat from the sun penetrates slowly. Carbon dioxide sublimes at lower temperatures than water. At 3 AU from the sun, carbon dioxide actively outgasses. Water remains mostly frozen. The crust blocks heat from reaching deeper water ice reservoirs, so the coma fills with CO2 while water stays locked inside. This matches some evolved comets in our solar system. 103P Hartley. 2. Kuiper Belt Comet. Shows high carbon dioxide, low water when far from the sun. Releases chunks of CO2 ice as it warms. Water does not fully activate until closer perihelion. Not some exotic alien star with wildly different nucleosynthesis. A normal star, a normal disk. But the conditions in that disk, temperature, radiation, location, those were different enough to produce this CO2-rich signature. July 20th, 2025, detected cyanide gas, atomic nickel vapor, no iron detected. That is unusual. Nickel and iron usually appear together in comets, same source, metallic grains. But 3I Atlas shows nickel without iron. The VLT kept watching through August. Nickel emission 4.6 plus or minus 0.7 grams per second. Cyanide emission 17.6 plus or minus 2.0 grams per second, both increasing steadily as the comet approached the sun. From 4.4 AU to 2.85 AU, the concentration climbed. Heat drives sublimation, more volatiles release, standard comet behavior, but the nickel without iron, still strange. Hydrogen cyanide production rate 1.5 plus or minus 0.5 times 10 to the 25th molecules per second. 2.33 AU from the Sun, activity increasing, coma evolving. By late August, images from Gemini South Telescope showed an anti-solar tail, 30 arcseconds long, pointing away from the Sun. Dust grains blown by radiation pressure. Typical comet tail. But earlier in July, Hubble saw a Sun facing plume, dust ahead of the nucleus, not behind. That happens when sublimation is strongly concentrated on the dayside, non-spinning nucleus. Or very slow rotation, hot front, cold back. Dust jets forward before radiation pressure sweeps it away. By August, the radiation pressure won. Tail developed, but the early asymmetry, that tells you about the nucleus spin state. Slow, maybe tidally locked to some ancient encounter. Maybe just primordial. The swift data implied water loss rate around 40 kilograms per second. Fire hose at full blast, as some press reports said. But the JWST data shows low water in the coma. Discrepancy, likely explanation. Most of the water detected by SWIFT comes from the coma, not the nucleus. Water ice grains ejected into the coma sublimate add to the OH signal. Makes the water production rate look higher than direct nucleus output, the actual nucleus, probably producing much less water than 40 kilograms per second. Maybe a few kilograms? Most of the activity, carbon dioxide. The size question loops back. David Jewett estimated mass loss drives the lower size limit. If carbon monoxide supplies the coma, the nucleus must be at least 0.22 kilometers radius to provide enough sublimating surface area. If carbon dioxide supplies the coma, it can be smaller because CO2 sublimates more efficiently. But the dust loss rate, 12 to 120 kilograms per second. That requires a certain amount of gas to lift the dust. The gas drags dust grains, accelerates them, small grains fast. Large grains slow. The observed dust distribution and velocities constrain the gas production. The gas production constrains the sublimating area. The sublimating area sets a minimum nucleus size, that minimum. Probably close to 0.5 kilometers, maybe 1 kilometer. Similar to 2I Borisov, not the giant. 4,022 position measurements from 227 observatories worldwide. May 15th to September 23rd. Upper limit on position shift 0.028 arcseconds. No detectable non-gravitational acceleration. For a comet producing 150 kilograms per second mass loss with outflow speed 440 meters per second, the lack of acceleration sets a lower limit on mass, 33 billion tons minimum. At solid density 2 grams per cubic centimeter, that implies minimum diameter 5 kilometers, close to the upper bound from Hubble. Loeb argues this means 3I Atlas is large, 5 kilometers or more, heavy, dense, not a fluffy rubble pile, but the assumption all the outgassing contributes to thrust. If the outgassing is isotropic, it cancels. If it is concentrated in jets that precess or wobble, the thrust averages to near zero over time. Non-gravitational acceleration analysis assumes steady directional thrust. If 3I Atlas has variable asymmetric jets, the acceleration could be masked, so the mass estimate uncertain. Cass's camera on TGO captured images, slightly fuzzy white dot, coma visible, nucleus unresolved. TGO designed for imaging Mars, surface from a few hundred kilometers, not optimized for faint distant targets. 3. I-Atlas, 10,000 to 100,000 times fainter than typical Mars surface features, but they got images, showed the coma, confirmed activity. Mars, reconnaissance, orbiter high-rise camera, planned observations, pixel resolution 30 kilometers at the flyby distance. The brightest pixel in high-rise images will give an upper limit on nucleus brightness. If the nucleus contributes significant flux to that pixel, you can constrain its size better. If the coma dominates, even at 30-kilometer resolution, then the nucleus is definitely small. Results expected, but not yet released as of October. Europa Clipper instruments might detect these particles, measure composition, isotopes, but the government shut down October 2025. Europa Clipper in cruise mode, not all instruments active. If shutdown not resolved by alignment window, the opportunity slips, measurements lost. Politics versus science, old story. If Juno has line of sight, it could image the post-perihelion comet, measure how perihelion passage changed it, how much mass lost, whether the nucleus fragmented. 2. I Borisov did not fragment, stayed intact. Will 3, I Atlas, unknown. 1.36 AU, closest to Sun, peak heating, maximum outgassing. Then it swings behind the Sun from Earth perspective. Too close to sun, glare to observe. Occultation window September through November. Ground telescopes lose it. Space telescopes can try but risky pointing near sun. Parker Solar Probe might see it, designed to fly close to sun, but pointing requirements, data downlink schedules, uncertain if it captured 3I Atlas during perihelion pass. Activity declining. Ground telescopes pick it up again. Hubble plans more observations. JWST scheduled for December follow-up. Measure post-perihelion changes. Did water sublimation increase closer to sun? Did the CO 2-to-water ratio drop? Did the nucleus crack? Did dust production surge, then crash? Comparing pre-perihelion and post-perihelion data, that reveals evolution, thermal response, structural integrity. Vertical velocity component suggests 3. I Atlas comes from the thick disk of the Milky Way. The thick disk contains older stars, 7 billion years old, older than the Sun, older than the solar system by 2.5 billion years. If 3I Atlas formed around a thick disk star and was ejected early, then it has been traveling through interstellar space for billions of years. Cosmic ray exposure, radiation processing, impacts from interstellar dust grains, all of that degrades the surface, builds an insulating mantle, alters the ice composition, destroys volatiles. 3I Atlas, possibly the oldest comet ever observed, possibly 3 to 14 billion years old per initial studies. The chemistry supports this. CO2 survives radiation, water does not. An ancient comet would lose water preferentially over time. What we see, CO2 rich, water poor. Escape velocity from solar system at 1.36 AU, 42.7 kilometers per second. 3. I Atlas moving faster, way faster. Gravitational slingshots during its interstellar journey. Every close encounter with a star, every passage through a molecular cloud, gravity tugs. Accelerates. Over millions or billions of years, the velocity builds. By the time it reaches our system, it is screaming. One-way trip. Hyperbolic excess velocity, 25 kilometers per second. After leaving solar system influence, it will coast through interstellar space at that speed until the next encounter. Might take millions of years, might never happen. Galaxy is big, stars are far apart. At those speeds, with those gravitational perturbations, impossible to pinpoint. David Jewett compared it to glimpsing a rifle bullet for 1,000th of a second. Cannot project the path backward accurately. Too many unknowns, too much time. 3. I Atlas could have been ejected from a star system anywhere in a volume of space hundreds of light years across, or more. The thick disk connection narrows it slightly, but thick disk stars number in billions. No way to identify which one. No way to calculate the exact ejection event. Giant planet scatter. Close binary star encounter. Supernova shockwave. Any of those could fling a comet into interstellar space. 3. I Atlas bears no ID tag. Just chemistry, just velocity, just the fact it is here now. 3. I Atlas is the third interstellar object confirmed in 8 years. Oumuamua, 2017. 2. I Borisov, 2019. 3. I Atlas 2025. 3 confirmed. How many passed unnoticed? Atlas, survey started 2015. Full operations, 2017. Zwicky Transient Facility, 2018. Pan-STARRS, other surveys. Before 2017, the sky coverage and sensitivity were not sufficient. How many interstellar objects zipped through between 1900 and 2017? Unknown. Could be dozens, could be hundreds. Small, faint, fast, easy to miss. Will detect faint moving objects. Predictions say Rubin will find 1 interstellar object per year on average, maybe more. The population models depend on size distribution. If most interstellar objects are small, like Oumuamua, then the detection rate goes up. If they are large, like early estimates of 3 I Atlas, then rate drops. The truth? Probably a mix. Power law distribution, lots of small ones, few large ones. 3 I Atlas if it is truly 5 kilometers. Rare. If it is 1 kilometer, more common. We need more detections to build statistics. Rubin will provide those detections. If another interstellar comet like 3 I Atlas appears and the geometry is favorable, Comet Interceptor could launch. Flyby mission, close approach, high-resolution images, in-situ measurements, dust collector, maybe even sample return if technology evolves. 3. I Atlas too early for Comet Interceptor. Mission not ready. But next time. If there is a next time within mission lifetime, that would be the breakthrough. Direct sampling of interstellar material, isotope ratios, organics, mineralogy. The data would revolutionize understanding of planet formation around other stars. 2 I Borisov, clearly a comet. Coma, tail, water and carbon monoxide detected. Carbon dioxide present, but normal ratios. Looked like a typical solar system comet, just came from outside. 3I Atlas, also a comet, but chemically extreme. CO2 dominated, water suppressed, ancient, processed. Evolved. The diversity. That tells you planetary systems around other stars vary widely. Formation conditions differ, disk temperatures, radiation fields, giant planet configurations. All of that affects what gets ejected, what survives interstellar space, what arrives here. The small nucleus, hidden in a bright coma. That is the key revelation. You cannot judge an interstellar object by its apparent brightness. Early estimates wrong by a factor of 10. The dust coma tricks you, makes the object look huge. Only high-resolution imaging separates nucleus from coma. And even Hubble, at the peak of its capability, cannot resolve the nucleus of 3I Atlas directly. The coma wins, the nucleus hides. The only way to measure it: model the dust, model the gas, fit the brightness profile, constrain the size from what it cannot be. Upper limit 5.6 kilometers. Lower limit 0.44 kilometers. Best estimate, probably 1 to 2 kilometers. Small, dense, old, CO2, rich, spinning slowly, wrapped in dust. Need resolved imaging. Need to separate the nucleus signal from the coma signal. Future surveys must account for this. Interstellar objects might be small but appear large due to activity. The population of small interstellar objects, probably higher than thought. The population of large ones, probably lower. The size distribution skews toward smaller, more small objects. They're just harder to characterize accurately. Efficient scattering at visible wavelengths. Reddish color, tholins, organic residue from radiation processing. The dust does not vanish quickly. Radiation pressure pushes it into a tail eventually. But near the nucleus, the dust forms a cloud, scatters sunlight, creates the teardrop glow Hubble saw. The dust particles, where do they come from? Nucleus, surface, ice sublimates, lifts dust. The dust was embedded in the ice, refractory grains, silicates, organics, maybe metal. When the ice goes, the dust floats free, gets blown away. Over millions of orbits around ancient host star, or during long interstellar cruise, the surface accumulated dust from various sources. Now it sheds that dust as solar heating warms the object. No resolved light curve. The brightness variations. As 3I Atlas rotates, would tell you the rotation period. But you need to see the nucleus, not the coma. The coma hides rotation. It is diffuse, changing shape due to outgassing, not rotation. Without resolved nucleus, rotation remains unknown. Could be hours, could be days, could be tidally locked. Spin measurement requires very high resolution imaging or radar. Radar from Earth. 3I Atlas too far, too fast, out of range. No chance. Maybe Mars orbiters during flyby could have tried, but unclear if they did. Massive. 3 observatories: Hubble, JWST, Sphere-X, ground telescopes, VLT, Gemini, Keck, Nordic Optical, hundreds of observations, thousands of spectra, imaging across wavelengths, ultraviolet to mid-infrared, dust maps, gas maps, composition, isotopes, activity curves, orbital refinement. The dataset on 3I Atlas will fuel papers for years, comparing to solar system comets, comparing to 2I Borisov, modeling formation scenarios, testing protoplanetary disk chemistry, understanding radiation processing, exploring comet nucleus evolution. All of that comes from this one object. And the realization, the nucleus is too small to resolve. That statement, that is not a limitation of Hubble. That is a statement about the object. At the distance and size and brightness of 3I Atlas, the nucleus subtends less than the diffraction limit. It is physically impossible to image the nucleus as a resolved disk with current technology from Earth orbit. You would need an interferometer, or you would need to get closer. Mars orbiters got closer. 30 million kilometers. Still not close enough for resolved disk. You would need to be within a few 100,000 kilometers. Close flyby, spacecraft mission. That is the only way to see the nucleus surface, to measure its true size, to map its shape, to understand what is really there under the dust cloud. When the next one arrives, do not trust the first brightness estimate. Assume a coma. Assume the nucleus is smaller than it looks. Get high-resolution imaging early. Get spectroscopy. Separate the components. Only then can you know what you're dealing with. Only then can you understand if it is a giant or a dwarf wrapped in a bright cloak. Traveling for billions of years, processed by radiation, wrapped in an insulating mantle, now warmed by the sun, shedding volatiles, casting off dust, creating an illusion of size. The illusion fooled everyone at first. Then Hubble looked closer, and JWST measured the chemistry. Then the truth emerged. Not a giant, a ghost, a chemical rebel, an ancient traveler carrying ice from a star system that may no longer exist, wrapped in a cloud of its own making, too small for resolved images, too bright to ignore. That is the true nature of 3I Atlas, a tiny visitor hiding in plain sight. By the time 3I Atlas exits the solar system in 2027, we will know more, but we will never know everything. The nucleus will remain unresolved. The origin will remain uncertain. The next encounter, billions of years from now, with another star in another part of the galaxy. We will never see that. 3I Atlas came. 3I Atlas will go. We caught it for 1 year, one brief moment in its multi-billion-year journey. And in that moment, we learned that size is an illusion, that chemistry tells the story, that ancient comets carry secrets in their ice, that interstellar space is full of these travelers, silent, invisible, until they cross our path and the sun lights them up. Then we see them, measure them, name them, and watch them disappear back into the dark,